Again, so welcome back to where we were discussing. So where we left off in the last video. In the last video, we were talking about dimensional analysis. And what about dimensional analysis? Well, we are trying to form dimensionless quantities using Buckingham's pi theorem or something like that. So we're going through that method a little halfway through. So we want to find some unitless quantity, and we have already we want these unitless quantities to cover all of these quantities that we have put over here. Okay, so we just want unitless quantities. All right, so we want unitless quantities to have viscosity inside. And we found that the units of viscosity were mass per length per time, as per in the last video. So I'm going to copy all of this over. Okay, so we're going to look at dimensional analysis part 3, which is this video. Dimension analysis part 3. And you go. Okay. Let's remove the underline and we can start. So that's where we left off. So first step, we want to get rid of the most simple things. Okay. We want to get rid of m. So again, let's copy down this. Okay, we found that we can get our units in this kind of a way. We have the units of our quantities here. So we need to get something to cancel out this m. What is the only thing that can cancel out the m? Well, it looks like rho can already cancel out the m. Okay, so rho can cancel out the m. So what is rho? ml minus 3, and we'll make it minus 1. Okay, good. So now what we have here, what is our units? We have gotten rid of m because this viscosity was to the first power, then we divided it by the density. What are we left with? We are left with time, because we have not touched it. Time. Okay, wrong. Time. Inverse of time at least. And we also have a length quantity, L squared. Why? Because 3 times minus 1, that is 2. Minus 2 is, or rather 3 times minus 1 is 3. When added to minus 1, it becomes 2. So the next thing we want to get rid of is time. Okay, so get rid of time, because length, we have a lot of things we can do with length. What are we going to do with time? We want to get rid of time, we need to use velocity. So velocity is inverse of time. So we will need to make this quantity to the minus 1 power, t to the minus 1. Okay. All right. So ml and t, ml and l and l and t. So what do we have after we well, we'll put this as minus 1. What do we have after that? L t to the minus 1. Then you inverse this. We have length remaining. So we can just, for simplicity's sake, take either pipe length or the hydraulic ring diameter. Either one is fine. Okay, so I'm just going to use the hydraulic mean diameter for reasons you shall see in a very short while. And that is actually length to the minus 1. Though in, of course, Buckingham pi theorem, you can do either of the one. Honestly, though I shall use the hydraulic mean diameter. Okay, so what is this unitless quantity? We have mu on top. We have mu on top. And what do we have at the bottom? We have rho. We have a velocity. And then we have hydraulic mean diameter. Okay. Now, we have one more because we have made use of many of these already. We have made use of a lot of these already. So dH, we have made use. Mu, we have made use. V mean, everything else here we have made use except area of the cross section. So this is pretty simple. A is just L squared. So the third, we can use L squared. We can use A, cross-sectional area, over L and DH to be our third unitless quantity. So we have 3 pi groups here. We can write K equals to some function of this one and this. So again, this is guesswork, but it's more refined guesswork. Okay, this is more refined guesswork. So instead of plotting K, maybe perhaps versus the pipe length or the velocity, you can pipe it. Yeah, no, you don't pipe it. You plot it against this value here. You plot it against this value here, and you plot it against this value here. And you still need to do experiments. So now, let's go to Perry's Chemical Engineering Handbook. I'll show you something. Alright. In friction factor. Let me look again. Can't remember where it is. Okay. Incompressible friction factor and Reynolds number. There you go. Wow. Look at this. Let's take a look. Okay, this is from Perry's. And take a look. We have this thing called the Reynolds number. And that is just equals to the inverse of this dimensionless number. So this dimensionless number is called the Reynolds number, and it's superbly important. So okay, rho V min dH over the kinematic dynamic viscosity. And of course, sometimes you'll see in fluids textbooks, they will give this thing called nu, which is called the kinematic viscosity. That is nothing but this mu over rho. So kinematic viscosity kind of takes the density of the fluid into account. So if you have that, we'll have just V min dH over nu. That's all. Okay. So you see that this Reynolds number is very important, and that is why I chose this dH. Well, because it's already been experimented on, and it's found that this combination of parameters in particular has been especially important, and you don't see really much else. Now, take a look at this K value, and take a look at this thing called the Fanning's friction factor. What do we see in there? So we have this friction factor, and it's equivalent, all right, to, what is this? D over L. D over L. So, and then it's multiplied by, you see the rho v squared at the bottom, 1 over rho v squared times delta p over 2 . Okay, is delta p over 2. Of course, if you want to make the bottom look like this, then all we have to do is just do this, and we'll be fine. So 4 over 2 is still 2 at the bottom. Okay. So what is this telling us here? Okay, this Fanning's friction factor is telling us the correlation between delta P, which is the pressure drop. Okay, pressure drop. It's the correlation between pressure drop, the kinetic energy term here. Sometimes they refer to half rho v square. They call it the dynamic pressure. Now, don't worry about it. This is just to introduce you. Don't need to think so much about it. But you see this D over L, L over D, however you want to put it. This DH over L ratio comes back. So this is very important as well. Now, what the experimental people have done, they've taken this Fanning's friction factor and plotted it against the Reynolds number. And look, all these beautiful curves that come out. For whatever your pipe shape, whatever your pipe size, all this data is condensed into this simple graph that you see here. So that's the very useful part of dimensional analysis. And how are we going to convert this friction factor into our K? So we have found K equals to, so we find that the energy loss per unit mass or volume equals to K half rho v square. Okay, we have found that this equals to the K times the half rho v squared. What can we do? We look at this half rho v squared here, we rearrange everything, and then we put it here. So we make half rho v squared the subject. Okay, so half rho v squared go on top. Equals to d by L times 1 over F times delta P over 4. So in fact, this is what our K would start to look like. So it's okay. Gee, maybe that's not a good way to use it. Let's go back. We have energy loss per unit volume. This is actually simply the pressure drop. Now it starts to make more sense. Okay. So the pressure drop, or in other words, the energy loss per unit volume, because PV is energy in energy units. So energy loss per unit volume equals to K half rho V squared. So this delta P is what we want to look for. Okay, so we make delta P, P the subject, and that will equal to 4 times half rho V squared times L over dH. Okay, 4 times half rho V squared. Okay, so 4 half rho V squared, L over dH. Any more? So this is moved over, this is moved over, this is moved over. All that's left is delta P. So delta P is done. And of course the fanning friction factor is on the right hand side. Now, so what is K? If we compare this and this, we'll find that the K of the pipe, specifically for any shaped pipes, that will equals to 4L F over dH. 4L F over dH. Alright, where F is this small f here equals the fanning friction factor. So this is the eventual correlation we come up with for pipes. And for this graph specifically, it's a circular pipe. So of course, if you want to estimate the friction factor for other pipes, you can just plug in the hydraulic mean diameter. Of course, there'll be some errors, but this is a good estimate to help us get started if we don't have any other kind of data. So let's zoom in. This is from Perry's Chemical Engineering Handbook. Alright, let's see what are some of the features of this graph. We see there are two distinct regions, one here to the left, one here to the right, where there's low Reynolds number here. It's a straight line, but it's kind of disjointed for a while. Then you see all these curves for different whatever these numbers are. Okay, so we see there are two regimes. One regime is that this number on the right hand side doesn't matter, and this regime here to the right hand side, these numbers start to matter. Okay, so what are these two regimes called? The left side is called the laminar regime, and the right side is called the turbulent regime. So if you see the fluids that's coming out of your tap, you see that the flow is very smooth, very well, I will call it very calming. I don't know how you call that adjective. It's very smooth. But if you think on the right hand side, you think of a tap when you turn it on full, and then it starts to you can't see through the fluid anymore. You can't see through the water. It becomes very frothy and all that. That's more like the turbulent regime. Okay, so let me zoom back out. Okay, so basically for any pipe, we just read off the F here, the fanning friction factor, off of this graph. We plug it in to get our K, because this was this was collated using the experimental data. Alright, then of course the DH and L, that will depend on the pipe length, and indeed it varies linearly with this the K varies linearly with the L over DH ratio, as we initially guessed. So that's experimentally proven as well. So what is this fanning friction factor? This is just, another dimensionless quantity that we find important, and yeah, it will help us to find our head loss or find our losses due to friction. So let's recap. It may have been a bit confusing, the last part. So what we find is that, okay, the dimensional analysis part is the part I'm highlighting. It's the more refined guesswork that we are talking about. We find that these dimensionless numbers could be important, but at least we have somewhere to start to try and experiment to see whether there's any correlation between this k and this dimensionless quantity. And then we say, okay, let's look at what other people have done in their experiments. And when other people have done their experiments, they have found that this Reynolds number is very important. So this, when you inverse it, 1 over this ratio, it becomes the Reynolds number. And that's very important. Okay, they found it out experimentally. I mean, you cannot guess it using Buckingham's pi theorem, but you have to do some experiments in order to find out which of these is important. And this Reynolds number is very important to help us correlate to k. And we can find k by looking at this Fanning's friction factor, because again, there are many ways to group up a lot of these dimensionless quantities, and this Fanning's friction factor is just one of those ways. And we have correlated our k term to this Fanning friction factor by just multiplying it by we have just done some algebraic manipulation to find how k is related to Fanning friction factor, and that will tell us, okay, oh right, if our tube is longer, we'll expect more head loss. Oh no, yeah, it's called head loss also, but I haven't introduced it yet. We'll cause more energy loss, and the larger the hydraulic mean diameter, the smaller the k. The larger the hydraulic mean diameter means that the surface to volume ratio is, yeah, that accounts for that. So with a larger Fanning friction factor, we will have more loss. So all these are found by experiments. So Fanning friction factor is just people, grouping k. Okay, these people grouping k, L by D, and then delta P half rho V square together. Alright, that's nothing more than that. It's just combining these terms to find a dimensionless quantity, a ratio, so to speak. So people plot this ratio against the Reynolds number, and they found experimentally that, hey, this works beautifully for pipes. So this is one of the most important graphs you want to see for energy loss in pipes. It's very important. So we can see that, hey, dimensional analysis has helped us solve the problem of having to do millions and billions of experiments. So for our 1,000-mile long pipe, okay, a 1,000-mile long pipe, let's say you want to ship oil or some other kind of fluid across the country, and we have never built it before, we cannot experiment with the pipe. We can just estimate its losses by going back to this. Okay, we'll just find the L, we'll just find the hydraulic mean diameter, and if it's circular pipe, we just find its diameter. We find this Fanning's friction factor. And how are we going to find the Fanning's friction factor? We're going to look at the Reynolds number, and we're going to look at the fluid density, fluid viscosity, fluid speed, and of course hydraulic mean diameter again. So this is a very important quantity to know. And we'll go look at this graph. It's either in the laminar regime or the turbulent regime, or somewhere slightly in between. If it's in the turbulent regime, we will need to know what these numbers are. Now I have not covered what these numbers are. They have something to do with the surface roughness of the tube. So if the tube is more, if you look at the microscopic diagram of the the micrograph of the tube surface. If you find that it's a lot more jagged, it causes the fluid to slow down more, then the surface roughness is higher. So some of the surface roughness you can find in the Penry's Chemical Engineering Handbook along the same chapter, chapter 6, or other chapters also if it's not there. But it's mostly in chapter 6 anyway, where fluids is. Alright, so this is how we usually talk about energy loss in the fluids context. And once we found out what our K value is, we can decide, okay, if I have this 1,000-mile long pipe, we have our fluid properties, we can start to design pumps, because now we can estimate the energy loss in the pipe. We can design pumps that can make up for this energy loss, right? You can design one pump here, one pump here, and let's see whether we have trapezoids. No, we don't have trapezoids. I don't see trapezoids anyway. Okay, so we have a pump. We have a pump. Okay, so we can start to design pumps. So this is one of our core problems in fluid mechanics. We want to do pump design. So this is one of the most basic information we will need, is the energy loss as the fluid flows from point A to point B. Okay, so it's a bit of a long video, but thank you for watching. I'll see you guys next time. Bye bye.